Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So what we will see today is Hastad's proof of lower bound for parity. Specifically, we will show parity not in AC0. In fact, we will show a stronger result that for all D and for sufficiently large n, any depth D circuit over and or not gates computing parity must have size at least 2 to the power 1/10 n to the power 1 over d. Okay. So, this is a exponential lower bound for parity. So, last class we also saw another lower bound, we also saw a similar lower bound for parity using the method given by Rasborov and later on improved by Smolensky. So, the lower bound that we had obtained was of the sort 2 to the power omega n to the power 1 over 2d. Okay. So, this is actually a stronger lower bound. This is actually, although this result was given before Rasborov's proof, but this is a stronger lower bound, okay, because we are getting a larger size over here. Okay. And in fact, this bound can actually be improved a little bit more. It can be improved to 1 over n to the power 1 over d minus 1, but we will just stick to 1 over d over here because it will make it slightly easier. Okay. So, the idea is that, so the point is that the proof technique of Rasborov and Hastad is completely different. So, the way Rasborov gave his proof was through polynomial approximation. So, what he had showed was that any AC0 circuit can be well approximated using polynomials, using multilinear polynomials and on one side, and then he also showed that the parity function cannot be well approximated by such polynomials, and then combining these two he got his lower bound. But the way Hastad gives his proof is completely different. So, we will give a idea. So, I will just I will very soon give a brief overview of the proof, how Hastad how Hastad's proof proceeds, but it is a totally different approach. And this approach, so this is the so Hastad's approach is through random restrictions. So, this actually also gives variety of other lower bounds. Okay. And similarly, even Rasborov's technique also gives several other lower bounds. Okay. So, these are like very independent techniques of proving lower bounds, both are interesting in their own right, but yeah, the problem that we are considering is the same over here. Yes, so that is another point. So, Rasborov-Smolensky's proof, in fact, the generalization given by Smolensky was much more, was saying much more than just parity. What they showed is that if you take any primes, if you take any primes p and q, okay, and let us say I allow my circuit in addition to AND, OR and NOT gates, also to have mod p gates, let us say, then it cannot compute the mod q function. Okay. For example, let us say if my circuit, if I allow the circuit to have mod 3 gates, even then parity is not computable, and not just 3, 3, 5, anything like that, and it can be generalized. So, that is a, I mean, the result can be generalized much more using the polynomial approximation method. Yeah, that is a good point. This method can be no, it cannot be generalized, or I do not know of any generalization to mod q functions for q bigger than 2, but there are generalizations for other functions like the threshold function. So, this actually can be used to give lower bound for the threshold function as well. So, that is something that I know, but yeah, for other primes I am not aware of, maybe it can be, but I am not aware of any such result. Yeah. Okay. So, let us see the proof structure, and then we can, I mean, discuss their pros and cons. Okay. So, how do we proceed? So, okay. So, firstly let me just start by giving a little bit of warm up examples. Okay. Some notations and definitions. So, let us start by talking about, so what do we mean by small depth circuit? So, let us say what are depth 0. So, depth 0 circuits are just literals. Okay. So, if I have just literals, it is very obvious that you cannot compute parity using depth 0. So, depth 0 circuits are just literals. Okay. So, by literal I mean a variable or its complement. Depth 1 will be what? So, depth 1 circuits will be are well, we are always talking about unbounded gates over here. So, they are just and OR gates. Okay. So, I just have one level. So, I just have one AND gate or one OR gate that is present. So, again parity cannot be computed by just a single AND or a single OR gate, because well, flipping just one variable of the input actually changes the parity output, but we know that for AND and OR gates that is not necessarily true. You can flip an input and still the output might remain the same. Now, what are depth 2? What are depth 2 circuits? So, depth 2 circuits are essentially either CNFs or DNFs. Okay. So, they are either AND of ORs. Okay. So, AND of OR means CNFs, or they can be OR of ANDs, which are DNFs. Okay. So, one more point is that if I look at depth 0 and depth 1 circuits, so not just parity, but there can be many functions. In fact, you can so parity is just one example, but you can show that there are several functions which are not computable using depth 0, depth 1 circuits. But the moment I go to depth 2, one can show that any function can be computed using depth 2 circuits, because I can write the truth table of that function and I can take the DNF. So, one way of doing it is just I take the OR of the rows which are ones and I get a DNF. So, in particular even parity can be computed using depth 2 circuit. But what about the size? Okay. So, immediately what we get as a result is okay. So, let me just write this as a warm up exercise, that any depth 2 circuit computing parity must have size exponential. Why do we get this? Because again, so depth 2 circuits, as I said, is essentially a CNF or DNF. Let us take just one, let us take, for example, let us say it is a DNF, the other proof is symmetrical. Now, for a DNF to compute parity, what can I say about each term? Okay. So, a term is basically a product of literals. What can I say about a term? How many literals must it have? Now, suppose a term has less than n literals, okay. So, which means that there is one variable which is absent in a term. Now, one can argue that such a function or such an expression cannot compute parity, because if even if one literal is absent, I can always flip that literal and the value of the parity would change, but here it does not affect the function or the circuit. Okay. So, if I have a depth 2 circuit, if I have a DNF circuit which has any term that has less than n literal, it cannot compute parity. Okay. So, the first observation is that every term, so these are also known as min terms, but anyway, so every term in a DNF circuit must have size or must have n literals. Now, how many terms must be present to compute parity? So, if I have the parity function, the parity function is basically 1 on 2 to the power n minus 1 many inputs. Okay. I must have at least I must have at least that many terms in order to represent parity, right. So, there must be 2 to the power n minus 1 terms present, because even if one term is absent, I can basically I mean for that setting of the variables, the parity function would not be computed correctly. So, each and every 2 to the power n minus 1 terms must be present on which the parity function evaluates to true, and therefore 2 to the power n minus 1 times n gives a lower bound of this form. Okay. Because if you look at the parity function is 1 on 2 to the power n minus 1 many setting of the variable. Okay. So, if I look at the truth table, 2 to the power n minus 1 rows are 1 for the parity function, right. Now, suppose I have a DNF expression or I have a DNF circuit on which even one of those terms is absent, right. So, if that particular term is absent, for that setting of the variable, the circuit does not evaluate to 1, but parity evaluates to 1. So, it is not computing parity correctly, right. And the proof of CNF is just symmetrical. So, instead of I can apply De Morgan's theorem, and instead of parity I can compute parity complement, and the proof is the same. Okay. So, this is just showing that I mean an easy way of showing that depth 2 circuit to compute parity must have size exponential, and if you go to depth 3, things get complicated. Okay. From depth 3 onward, the proof is no longer such simple, and what we will show is that we will show it for arbitrary but constant depth. Now, one more thing that I must define here is CNFs and DNFs with a fixed number of terms. Okay. So, let me call it T. A TCNF is a circuit where the last level gates have fan-in bounded by T. Okay. And similarly, we can define T DNF. So, basically if I have a T CNF, it means that every clause has at most T literals, and if I have a T DNF, it means that every term has T literals. Okay. So, now you can see that, well, if I have a T DNF where T is smaller than n, okay, for example, if I have a n minus 1 DNF, clearly it cannot compute parity by this argument, because every DNF, every term must have all n literals, and the same thing over here. Okay. So, this is the idea. So, we will show that a restricted form of DNF or CNF will be used to give the lower bound. Okay. What else? Okay. So, next I would define a what is called a random restriction. So, we have actually used random restriction in Nechi-Porrak's theorem, but I will define it once again. So, for P in 0 1, a random P restriction rho is defined as follows. So, for all variables xi independently, how do I write this? Okay. I don't have to write Excel. Actually, I don't need to. Probability that xi is unfixed is P, probability that xi is, let us say, set to 1 is 1 minus P by 2, and probability xi is set to 0 is again 1 minus P by 2. So, this is basically a partial assignment. Okay. So, I have my n literals. So, a random P restriction is a partial assignment to the variables x1 up to xn, which is defined as follows. So, for every variable xi, with probability p I just leave it as it is, and with probability 1 minus p by 2 I set it to 0 and or 1. Okay. Okay. So, next is a what we will use here is a circuit in a canonical form. So, a circuit is said to be in canonical form if it is a formula and the levels of the if it is a formula partitioned into layers such that the layers alternate between and or gates and we have literals at the bottom. Okay. We will call the but last size of a circuit is the number of gates is the total number of gates in the except for the last layer. Okay. And the bottom fan-in of a circuit is the maximum fan-in in the last layer. Okay. So, let me give a quick example to demonstrate these terms. So, suppose I have a circuit which looks like this. So, I have AND, OR, then I have let us say 2 ANDs, and let us say I have some literals over here. Okay. So, they can be anything. So, x1, let us say x3, x2 bar, x4 and so on. Okay. So, this if I have this circuit, so now so this is a circuit in canonical form, okay, because it is a formula as you can see. So, a formula is basically a circuit whose fan out is 1 at most 1, and the levels alternate between AND and OR gates, and the literals are at the bottom. The but last size of this circuit will be 4 over here, right. So, the but last size here will be equal to 4, 1, 2, 3 and 4. Okay. So, it is basically the size except for the last layer, and the bottom fan in this case will be well 3, right. So, what is the maximum? So, I have 3 over here, 2, 2, 1, 1, 2, 1. So, the bottom fan in is 3. Okay. So, it is the size of the circuit except for the last layer. So, 1, 2, 3 and 4. Okay. Now, the question is, can we transform any circuit to a circuit in canonical form? Okay. So, the answer is yes, you can transform any, you can convert any circuit into a formula, and then given the formula you can always make sure it is layered in this manner. Now, the point is how much is the blow up in size, that is what we are concerned about. Okay. So, one can actually show that the blow up in size, so if the depth is constant, then the blow up in size will just be polynomial. Okay. So, if let us say the initial size was some m, then the final size will be some m into n to the power k. Okay. So, that k will actually depend on d, okay, but because d is constant for us, it will still be polynomial. And in fact, this is also an exercise in Arora Barak's textbook, that how can you convert first of all a circuit into a layered circuit, and secondly how can you convert a circuit into a formula in this form, or how much is the blow up. Okay. So, you can actually try that, but yeah, it is actually not very difficult. So, essentially what you do is that if you have a gate which has fan out more than one, you just make 2 copies of it, you just make 2 copies of it and you keep on doing it. Okay. So, you make that many copies of it, that is okay. So, even then, so that is what I am saying. So, one can show that because the depth is bounded, the blow up will still remain polynomial in the original size. Huh? We are only looking at constant depth. So, the blow up will actually be exponential in the depth. Okay. Now, because the depth is constant, therefore, it is, the blow up is polynomial.